A very good day to all of you. My name is Ishan Sharda and I'm a fourth year computer science student at Manipal University, Jaipur. In this video, I'll be presenting one of the most revolutionary ideas in modern natural language processing, the self-attention mechanism. Self-attention forms the mathematical core behind powerful language models like transformers, BERT, and GPT, which today drive very large systems such as ChatGPT and Google Gemini. We'll understand what self-attention means, how it works through query, key, and value vectors, and why it completely replaced older sequence models like RNNs and LSTMs. By the end, you'll see how this mechanism allows machines to truly understand context in human languages. So, we have attention, which is a concept that teaches machines how to focus on specific parts of the input data. Because not all the parts of the sequence are as important as every other part. Some words in the text sequence can be very important for understanding context and patterns and relationships and so on, and some words might not be that important. So, attention mechanism specifically is a type of neural network that actually allows a machine to achieve this. It does so by recording different weights for every input it gets in different epochs, and when the weights are perfectly set, any input given to it, it is able to capture context and patterns very efficiently. This makes the model better at understanding very complex relationships and long term dependencies in the data. So, here we have a brief history of attention mechanisms. We see in the 1990s we had simple methods like filters, and as we approach the 2010s, we had non local methods like kernels. And as we approach the modern NLP era, we had a major breakthrough with the sequence to sequence model, which used RNN as an attention mechanism. And as we get to the birth of the transformer architecture, we see that attention was fully conceptualized as a mathematical concept. This was a major breakthrough. So, why self attention? Before self attention, NLP systems relied heavily on RNNs and LSTMs, which process text one word at a time. Every next word in the sequence was predicted only by looking at the last word in the sequence. So, all the other words before it were not captured properly. So, firstly, there's a sequential bottleneck. Computations cannot run in parallel, making training extremely slow. And secondly, RNN struggled with long term dependencies. When two related words are very far apart in a sequence, information fades as it moves through the network. For example, I have a sentence: the animal didn't cross the road because it was tired. Older models forget that it refers to animal. Thirdly, there's a limited context. Each word understands only its nearby neighbors. Self attention solves this by allowing every word in a sequence to look at all the other words in the sequence instantly. So, here's the solution. The term self means that attention is applied within the same sequence, and each word attends to all other words. This creates attention scores for every word respect to every other word that measure how one word should focus on another word. The final output for each word becomes a weighted combination of all word embeddings in the sequence. This is a proper context aware representation. For example, if I have a sentence, the bank will not approve your loan. The word bank pays higher attention to approve and loan, realizing we're talking about a financial institution, not a river bank. And we have three key vectors. Every word embedding is projected into three separate vectors: query, key, and value vectors. You can think of them like this. Query says, what am I looking for exactly? Key says, what information do I have currently? Value provides, here's my actual meaning. To find out exactly how much one word pays attention to every another word, we take the dot product of the query vector of that word with the keys of all the other words. This produces attention scores for that word with respect to all the other words. These attention scores are then normalized using a softmax function, which turns them into probabilities that add up to 1. Finally, these weights are applied to value vectors, producing a new context-rich representation for each vector word. So, here we have a small example. A fluffy blue creature roamed the woodland forest. These are the original embeddings. So, an embedding is nothing but a vector with many dimensions. One dimension is for the binary representation of the word. Say fluffy is represented as 0, 1, 0, 1, 1, etc. Blue is represented as 1, 1, 0, and so on. This can be reserved in one dimension, and we can have many other dimensions. Say I have 12,000 dimensions. Other dimensions can be reserved to capture the global context, relationships, semantic meanings, and other details about one word with respect to all the other words, such that we get new embeddings. The original embeddings will only have, say, the binary representation of the word. We want new embeddings that capture a global representation. So we just provide the text sequence. The images are for our reference, and after when you get the new embeddings, E4 prime, which was originally E4, which represented creature as a simple orange object, will now infer that fluffy and blue already make this creature fluffy and blue. So this is the first step, having these input vectors, input embeddings, these ones, and weight matrices, which will look. We have weight matrices for query, key, and value, all the three. In the next step, we have a query key interaction. If we see here, we have our original embeddings. We multiply them with the weights of key weights and query weights. And the query exactly over here is that are any adjectives in front of the word creature. So yes, fluffy and blue are there. So how does the machine actually figure this out? So when we take the original embedding and we multiply them with the weight, key weight and the query weights, every embedding is multiplied. We get this query vector and key vector for each embedding. Now, when we take the dot product of this key and query vector, we get how similar they are. Or if they point in the same direction, that means they have a similar relation. If they point in the opposite direction, they have a opposing or different relation. That is the core idea. So here we compute the attention scores, that is the dot products. Some dot products are higher, some are lower. And if we see, for creature, fluffy and blue dot products are highly high. That is, fluffy and blue dot products are very high. Attention scores are very high for them. This process is exactly called as attending to. Other scores may be smaller, others may be higher. This is how exactly relationships are captured, and this is the core computation behind the self-attention mechanism. Next, we scale all the scores such that they don't have very large values and are efficient for computations. Then we also do this by dividing all the attention scores by the square root of the dimension of the key matrix, key weight matrix. And then we apply a softmax so that it gets converted into a probability distribution between all the scores are between 0 and 1 and they add up to 1. So the next step is softmax function, which we just saw, and in the weighted value vector. So if you see here, we have this orange creature, or this creature by default, and we have a fluffy creature. So is there any way, this is the creature embedding, this is the fluffy creature embedding, is there any way I can add a vector to this so that I get fluffy creature? Yes, there is. If I take the fluffy embedding and multiply with the value matrix, I get this value vector, which when I add it to creature, so when fluffy is added to creature, I get fluffy creature. So each value vector is multiplied by its respective attention weight. This step ensures that important words contribute more strongly to the final output. This is what exactly is happening over here. So here was our original embedding, and we get the new embedding, and we added the value vector to it. We do this for all the other embeddings. We get the new set of embeddings from the original set of embeddings. This is just one head of attention. One self-attention layer can capture some relationships, but not all of them. So transformers use multi-head attention, meaning multiple attention operations can run in parallel. Each attention head has its own set of Q, K, and V matrices. So each head learns a different type of linguistic relationship, meaning every attention operation can run in parallel, each with their own set of query, key, and value matrices. Each head term learns a different type of linguistic relationship. One might capture grammatical structure, another might track pronouns, another might handle sentiment. This also helps because we have many dimensions in the embedding, around 12,000 say. After processing, the outputs of all the heads are concatenated linearly and transformed to produce the final vector. Then summing up the weighted vectors, we sum up all the weighted value vectors to form a single output vector for each word. This new vector contains information from all the other words, giving the model a context-aware representation, so it can use in the next layer. So through these 6 steps, self-attention transforms a simple list of word embeddings into a rich, contextualized representation that can capture meaning across the entire sentence. So why self-attention has completely replaced RNNs and LSTMs? It supports parallel computation, captures long-range dependencies, avoids vanishing gradient problem, and provides interpretable and attention weights. This helps us visualize what the model focuses on. Together, all these advantages make self-attention the most powerful mechanism for language understanding ever created. So, to conclude, the self-attention mechanism revolutionized how machines learn to understand languages. This concept forms the backbone of the transformer, the model architecture behind BERT, GPT, and today's AI revolution.